At 3:47 a.m., a second burst from Andromeda slammed Earth's magnetic field, compressing it by 2,000 kilometers. Detected across 3 continents, it was 50 times stronger than the first. AI systems failed to classify it. This wasn't just a cosmic signal, it was an event, and Earth just felt the impact, the return signal, the arrival of Wave 2. At 3:47 a.m. Eastern Time, radio arrays near Manitoba, Canada, lit up with an alert unlike any in recent memory. The raw intensity was enough to trip safety thresholds. Within seconds, confirmation rolled in from observatories in New Mexico and Western Australia. All 3 instruments pointed to the same origin in the Andromeda galaxy, just like they had 18 months ago. But this time it was different. The burst wasn't just stronger, it was staggering. 50 times brighter than the first, sustained for a full 3 seconds. For any fast radio burst, that duration is nearly unheard of. Most fast radio bursts flash and vanish in milliseconds. This one stayed, and in doing so it immediately rewrote expectations. Automated AI filters trained on thousands of past events couldn't categorize it. The classification system simply failed. This wasn't just an anomaly, it was off the map. It didn't match any astrophysical signature in the system's memory. The detection wasn't quiet. The raw data stream flooded internal networks, forcing manual override. "We thought it was a glitch," said Dr. Helena Cruz, systems operator at the Canadian Array. "But 3 locations simultaneous, that's not noise." The story begins here, not with a theory, but with a blinding 3-second pulse from 2.5 million light-years away. And in its wake, a pattern was reborn. A signal once written off as random now had a sibling. Something was repeating, and it wasn't just coincidence. "Every rule of deep space radio says this shouldn't happen," said Cruz. And yet, it did. Ghost echoes revisiting Wave 1. The story of Wave 1 begins on a cold morning, January 17, 2024, marked in archives as FRB 24117. At the time, it was just another entry in the growing catalogue of fast radio bursts, short, bright, and easily forgotten. It lasted 5 milliseconds, carried no repeat pattern, and showed no standout traits. Astronomers logged it, published it, and moved on. But everything about that first pulse feels different now. When Wave 2 arrived in October 2025, scientists reopened the data. This time, they didn't just study the radio signature. They pulled magnetospheric records, satellite telemetry, and ground-based readings. Buried in that archive exactly 8 minutes after the 2024 event was a faint, unexplained flicker in Earth's magnetic field. At the time, it drew no attention. The blip was minuscule, a few nanoteslas of deviation on one of NOAA's polar monitors, but with hindsight its timing was too perfect, the correlation too clean. It was as if Earth had flinched in response to something cosmic brushing past. "It didn't fit the profile of a solar flare," said Dr. J. Kim of the Goddard Space Flight Center. "No sunspots, no coronal mass ejection, yet there was this pulse right after the burst. What once looked like random noise now forms the first note in a pattern, a whisper before the shout." 2 signals, 18 months apart from the same Andromeda coordinates, forced scientists to admit this wasn't coincidence. "We always think the sky is silent unless it screams," said Kim, "but sometimes it whispers." And now we're finally listening. As researchers turned their focus to this new burst, one detail stood out above all others: its polarization, the strange rhythmic twisting that no known source can explain. If brightness was the first shock, then polarization was the second. In radio astronomy, polarization refers to the twisting orientation of radio waves, usually messy, random, or at best, slowly drifting. But the signal from Andromeda, this second wave, was doing something entirely different. It was flipping cleanly, rhythmically, every 200 milliseconds. Not drifting, not chaotic, just flipping, as if something were tuning it on and off with mechanical precision. Across all 3 observatories, Canada, New Mexico, and Australia, the same polarization pattern emerged. Scientists were stunned. Nothing known in nature behaves like this. Magnetars' polarizations wander. Pulsars can be sharp but not this precise. Plasma lensing and interstellar clouds might bend and scatter polarization, but not flip it in a perfectly timed beat. AI systems flagged the anomaly first. The filters weren't even looking for polarization signatures, yet they paused the classification pipeline because of unnatural ordering. The wave wasn't just strong, it was organized. "It's not the power that scares us," said Dr. Amina Solano, a signal analyst from the VLA. "It's the rhythm. Rhythm implies control. This wasn't just another cosmic flash. It was doing something, turning, flipping, repeating. And all that led to a more unsettling realization. Something disordered might not be random at all. At 3:51 a.m., just 4 minutes after the burst's arrival, Earth's magnetosphere, our protective magnetic bubble, twitched. Instruments on board GO satellites recorded a sudden inward compression. The shield shrank by 2,000 kilometers, pushing closer to Earth than normal. At first, scientists assumed a solar flare was to blame, or maybe a coronal mass ejection. But solar monitors were silent. No flares, no eruptions. The sun was calm. Only one event matched the timing: the Andromeda signal. It was impossible. A radio wave, just energy in space, shouldn't be able to affect Earth's magnetic field. Radio waves don't carry enough momentum. They don't interact with planetary magnetic layers. Yet the timing, the global consistency of the data, and the lack of other causes forced scientists to consider the unthinkable. If we had no solar activity, no known particles incoming, nothing else in the space weather logs, said Lieutenant Mark Reyes, who monitors NOAA's Space Weather Prediction Center. And still the magnetosphere responded. Was it coincidence? Was it some exotic interaction never before recorded? Or was the signal not just light, but something more? "It felt like someone knocked on the door," Reyes said, "and Earth reacted. What was once a cosmic curiosity was now a potential planetary interaction." This raised the scale of the event, from mysterious to dangerous. And if the wave could touch Earth's shield, then we had to ask, just how powerful was it? The numbers don't lie. At peak, the signal strength hit 140 Janskis measured directly at Earth's surface. That's not just high, it's unprecedented. For context, the brightest fast radio bursts ever recorded barely reached 3 Janskis. This wave was nearly 50 times stronger. Radio waves, like all light, fade with distance following the inverse square law. So if something this intense is reaching us from Andromeda, 2.5 million light-years away, then the original energy at the source had to be mind-bending. Calculations show it released more radio energy in 3 seconds than our sun emits in an entire hour. That's not an exaggeration, that's math. The kind of output we only see in rare cataclysmic events like neutron star collisions or hyperflares from magnetars, but even those don't match all the features. They're too fast, too random, too messy. "There's no known source that checks every box," said Dr. Kira Lennox, astrophysicist at Caltech. "Power, structure, repetition. This shouldn't be possible, but it is." The more scientists ran the numbers, the more the scale became impossible to ignore. This wasn't just loud, it was off the charts. A true cosmic super event. And that led to the next question. Was it just energy or was it language? What finally pushed this event beyond the edge of normal wasn't the brightness. It was the structure. Within the 3-second pulse, scientists detected timing clusters, tiny pulses within the wave. The main pattern, a 43-millisecond pulse followed by 86 milliseconds of silence, then 172 milliseconds, then it repeated. That's not noise, that's binary doubling, a signature of mathematical intention. 12 clusters, each showing the same internal doubling. This wasn't just repetition, it was precision, the kind of rhythm you might expect from a machine or a language. Natural phenomena don't repeat like this. Not exactly, not down to the millisecond. Pulses spin, but their intervals drift. Magnetars flare, but never in clean binary progressions. Even harmonic plasma echoes, a leading natural candidate, fall apart under this level of scrutiny. The breakthrough came from AI, not traditional software, but deep neural networks trained on pattern prediction. The AI flagged the doubling structure, noting that it exceeded randomness thresholds for natural events. "It's like hearing a heartbeat in the static," said Dr. Ayan Malik, head of the AI team at MTRE Labs. "You know it's not natural because it's too perfect."